Hey everyone, Amin here with AI Plays. Today we're covering auto white balance gain control. Let's get started. To recap, so far we've covered how a camera converts light into a Bayer domain image, how to correct dead pixels, how to compensate for black levels, how to adjust lens shading, and finally, how to apply an anti-aliasing filter. Auto white balance gain control is another type of correction applied to adjust for issues in camera light sensitivity. See, the way light is focused through lenses causes camera sensors to be inherently sensitive to a wide range of colors, but their response can vary depending on the light source. Because of that, an image captured under a specific light source can have a color cast. For example, an image taken under incandescent light might appear too yellow or orange, while one taken under fluorescent light might have a bluish tint. This phenomenon can be summarized by the term color temperature, as you can see by the image on screen. Different light sources have different color temperatures, which impact the final tint that shows up in the finalized color image. Auto white balance gain control works to mitigate the effects of this color temperature to produce a lifelike and realistically colored image, regardless of light source. This is the formula for auto white balance gain control. The gain values are calculated by dividing the average value of all pixels in a channel by the average value of all green pixels in the channel. Calculating these averages would literally involve taking the sum of all red pixels, then dividing by the total number of red pixels. Notice, this is going to cause the green gain to be 1. The reason we base the gain values off of the green channel is that the human eye is most sensitive to the color green, and there are the most green pixels in the Bayer domain image. Once you have the gain values, you can compute the corrected pixel values by multiplying their respective gains. When it comes to the code, you could use a brute force method with for loops. We'd initialize variables like red count and red sum to calculate the total number of red pixels in the image, as well as the sum of all red pixels. Then we could use the same technique as in black level compensation to locate pixels of the associated colors, and add the count to the total count variable and total pixel value. Then you could compute the average by dividing the sums by the total counts and compute the gains. Finally, you could loop through the entire image again to apply the gains to each pixel. The thing is though, this method doesn't really work, and we can see why if we add this print statement to print out green sum and green count. When we run the function on this small 50 by 50 section of the image, the value of green sum is over 900,000, while the value of green count is 1,250. Remember, in the entire image, there's over 24 million pixels. Half of them are green, which makes for about 12 million green pixels. At a very rough estimate, the total value of green sum should come out to be somewhere around 10 billion. And this is where the problem is. Even if we could ignore the amount of time this method would take, analyzing each of the 24 million pixels twice, these numbers are just too big and you end up with overflow errors. Now, there is a method to avoid using for loops, and it involves a method of indexing called numpy slicing. I've briefly mentioned slicing before when I introduced the fast ISP, and I'll give a short tutorial on the basics of slicing here. Slicing allows you to multi-select a certain range of indices from a numpy array. You use square brackets after an array as normal, but instead of one number, you use colons to signify the start, end, and step. Very similar to how you set dimensions in the range function for for loops. Additionally, leaving a blank field sets it to the default, where start becomes the beginning of the array, end becomes the final value in the array, and step becomes 1. How is this useful? Say for example you set your slicing coordinates for both the rows and the columns of a 2-dimensional array to start at 0 and end at the end. But the step is 2. This is going to create a new array, and it will extract every other row and column index. But another way, you would start at the 0th row and pull the 0th column, then the 2nd column, and the 4th column, since the step is 2, and all of the rest of the even columns. Then repeat this for all of the even rows. Recall from video 3 on black level compensation that if the row and column index are both even, you're handling a red pixel. And just like that, you can use numpy slicing to extract all of the red pixels into a new array. Similar slicing techniques allow you to access the green on red row, green on blue row, and blue pixels. Then you can put them each in their own separate arrays. From here, you can compute the average and gain values very simply just by using np.mean. After that, all that's left is to apply the gain values. and then you can reconstruct the image. This can also be done using numpy slicing for indexing, just in reverse. This technique lets auto white balance gain control run very fast, taking less than 1 second. Additionally, you can visibly see the difference after running auto white balance. If you use plt.imshow on this 50 by 50 section of the untouched bare image, you get this checkerboard pattern. However, if you apply auto white balance to the same section of 50 by 50, you can clearly see the effects. Evidently, the checkerboard pattern has been smoothened quite a bit, but the main benefit of auto white balance reveals itself once we create a color image, which will be the topic of the next video, color filter array interpolation. And that's it for today. Next time we'll cover color filter array interpolation. Have a good day, everyone.